Hello and welcome. Solutions for Jacobs book, Chapter 7. We're in the manufacturing processes. Homework questions 8, 9, and 10 we'll solve here. So, question 8 states a book publisher has a fixed cost of $300,000 and variable cost per book of $8. The book sells for $23 per copy. So, the first question, how many books must be sold to break even? That means at what unit have our costs equaled our revenues? We have to show where these two slopes or these two equations intercept. So the first thing we'll do is draw our revenues. So we might draw, it's $23 per book, and this is our revenues. It's going to assume that's a straight line, and the slope of that is 23. Okay, so that's our sales and our revenue. Same thing, using the term. And then our equation for costs say that we have a $300,000 fixed cost. That's why we're up on the x-axis, on the y-axis here. We're going to look for the point where the cost and the revenue curves intersect. And when we find that out, what we're looking for is on the x-axis, how many units do we have to sell at this break-even point? So the first equation for the first line is simply 300,000 plus 8x. Slope on this line is 8. Okay, slope on this is 23. And at the point where they intersect, those are going to be equal. That's the equation. We'll solve for x. How we do that is we subtract out our 8x. That goes to 15x. The next step would be divide both sides by 15. And you'll find that x is equal to 20,000. Okay? So the point on our x-axis that for the break-even that we just calculated is going to be 20,000. Okay? So there's a couple other things when we look at sensitivity analysis. Let's try looking at this problem. The next B and C are going to move a couple of these things around and say, what if we switch them around a little bit? What happens if one thing changes? How does that affect our break-even point? So let's go back to that. The next question is, if the fixed cost increased, would the new break-even point be higher or lower? So let's go draw that curve. Okay. Try to pick another color as blue here. Okay. All that means is that let's say it costs $400,000 in fixed costs, but our variable cost is going to be the same. That means it has the same slope. Okay, so we're assuming that the variable cost of $8 is represented. It's going to be a parallel line to our first, and our fixed cost over here went to $400,000. Okay, the first one is $300,000. That's our fixed or some cost up front to get started. And what did that do? Okay, so our first break-even point was right here. That's 20,000. And it's pretty obvious by just using the graphical method here. It's really great to use these graphs. Is by increasing the fixed cost, we've increased the number of units it takes to reach break even. It's just going to take longer to recover that $100,000 difference here. Okay, now let's take a look at C. They're going to ask us something different. If the variable cost per unit decreased, would the new break-even point be higher or lower? So now we're talking about the variable cost, not the fixed cost. This is the other part of sensitivity analysis here. There's two things we can change. And actually what I'm going to do is I'm going to remove what we already did so it's a little clearer here. We're going to draw a new curve. So we're assuming that we're going to start out at $300,000 fixed cost, but our variable cost, if it went down, if it only cost us $6, let's assume that the new curve is only $6. That says the curve is going to look like this. This is our new line. We're going to start at the same fixed point, but we have less of a slope here because each book might have only cost $6. Okay, and what did that do for us? Okay, so something we should be able to see here is, excuse me, what we see here is that the break-even point is less. Okay, so if the variable cost comes down, that's this shallower curve, then the intercept on the x-axis is going to be something less. Okay, so that's problem 8. Welcome back. This is objective problem 9 out of Jacobs chapter 7. We're in manufacturing processes. We're talking about break even, and this question has a little bit of a confusion factor to it. Confusion factor you have to remove to be able to solve it. The way that it was worded throws a little bit of a confusion factor into this. A manufacturing process has a fixed cost of $150,000 per month. Just ignore the per month part. That doesn't really take place anywhere inside the solution for this. Just like our last problem 8, just assume that our fixed costs are $150,000. Each unit of product being produced contains $25 worth of material and takes $45 of labor. So all we're going to do is say the combined cost of these two things is $70 per unit. That's your variable cost. How many units are needed to break even if each completed unit has a value of 90? So let's go over to our graph, our curves here, and we'll draw in the revenue curve. We'll do that in black. So this is our revenue curve, and the slope of this will be 90. We're selling the units at $90 a unit. The other equation that we have for the cost side says we start with a $150,000 investment or fixed cost or some cost even. And the combined cost of each unit is $70. That was $25 in material and $45 in labor. Okay. So we're trying to solve for this. We're trying to find on our x-axis how many units where these two things meet. That's our revenues or sales curve, and our cost curve where they meet our break-even point. So our equation is going to be, I'll just label our axis over here at 150,000. So we have 150,000 plus 70x equals 90x. Start solving for this. And as we do, we get 150,000 is equal to 20x. All we did was subtract 70x from each side here. And then we divide both sides by 20. 20. So we end up with x is equal to 7,500. We have to sell 7,500 units to break even. That's all there is to this problem. I think we don't have to answer anything more about that. They just want us to think a little bit more in labor plus material costs for the units. Thank you very much. Welcome back. Now that we've solved problems 8 and 9 from Jacobs chapter 7, we'll go ahead and solve chapter 10. This is where the questions came out, especially on C. Starts us out as many of the other problems have started out, and then it turns into something we have to do some thinking of. Assume a fixed cost of $900, a variable cost of $4.50, and a selling price of $5.50. They jump right in. They're not telling us what we're making here. We don't even know if it's books or bicycles, and it doesn't matter. We could actually just look at this as a generic problem, and we'll solve it using the steps that we've used previously. Let's go back to the graph, and we'll put in our sales in red. We'll show our sales curve here. So that's our sales curve, and the slope on that was 5.5. Okay, so the slope on that line is 5.5 for every unit we sold them for $5.05 or $5.50. That's the slope. The cost curve we'll put in as black, and we told it starts at $900 of investment and comes out like this. We've got to solve for what's the break even. The first part of the problem is what's our break even down here. Okay, so we're getting pretty good at this. Let's see, we'll make that 4.5 so we remember what those lines mean. And where the two lines meet is where 5.5x is equal to 900 plus 4.5x. And if we solve for x, we just subtract 4.5x from both sides, and x is equal to 900. Nothing particularly difficult with that one. There we go. What's the next part of the problem? I'm going to clean this up really quickly here because I need space to write when we come back. Let's see where we are here. Come back. Second part of it, part B, how many units must be sold to make a profit of $500? And what we need to do is just subtract sales. We'll subtract from sales the cost involved at any level of units that we produced. Okay, that's simple accounting. We're just subtracting costs from sales here. That's all it is. So we know that we're going to be to the right of 900. It's going to be some number greater than 900 is going to give us a profit of 500. Okay, go back to our pen, and that says $500 is going to equal 5.5x minus 900 plus 4.5x. Okay? And so we just do a little solutions here. This is going to turn out to be x minus 900. And solve the rest of this. X is equal to 1400. Okay? So 1400 units gives us a profit of 500 somewhere out here. Okay? There we go. I'm going to leave that up, however messy it might be, and we're going to use this area down here to solve the next part of the problem. It's related to that. That's why they're giving us progressives here, so we can use what we just came up with to figure out how many units must be sold to average 25 cents profit per unit. And then they ask us about 50 cents per unit, and even $1.50 per unit. So there's three things we have to calculate here. We'll go back to this. And if we read the question and then convert it into an equation here, go back to using the pen, and we said, on average, the average number is going to be 25 cents per unit. And if we just go by definition, we're going to try to find the level of sales, the number of units where the sales minus the cost. We're going to try to find the intercept in this line where that divided by the number of units. That's how you get your average. Your average comes from the cost divided by the number of units. If we go just by that definition, we can rewrite our equation that we had before. I'm going to fix that for a second here. Sorry about that. Go back to our pen. And the equation what we just used is, what's our profit? It's going to be 5.5x minus 900 plus. It's not giving them my decimal point. 4.5x. Okay, so that's the sales curve minus the cost curve. Just divide that by the number of units. That's going to be the average cost per unit, right? Or the average profit per unit. If we solve that out, we can multiply both sides by x. And that's going to be x minus 900. And when you solve for that, you end up with 900 is equal to 0.75x. Multiply or divide both sides by 0.5x, and you should get 1,200 units. Okay? What they do is they ask us to solve then again for 50. Okay? Let's clean this up a little bit. See if I can get rid of some of this down here. Okay, we have to get rid of all that. Let's just do it all over again. Bear with me on this. I just got a new tablet, so I can do this with my classes. I can actually write in whatever horrific font I'm using right now. But we're going to resolve this for 50 cents average per unit. So we're saying the average is 50, 5.5x minus 900 plus, that's 4.5x divided by x. And now we end up with a 0.5 equals x minus 900. And we ended up with 0.5x equals 900. And it won't be till we get out to 1,800 units that we're actually averaging 50 cents. We just resolved it for that. And finally, we'll do it for $1.50. Get rid of that. Get rid of a few of these ticks here. And if we solve that now for $1.50 per the average is $1.50, 5.5x minus 900 plus 4.5x all over x. So if we end up with 1.5x on this side is equal to x minus 900 here, we may end up into an interesting situation. You're going to see what happens here. And so you're going to end up with 900 is equal to a negative 0.5x, and it comes out as an insolvable equation that way. And there will never be a point where there's $1.50 is going to be the average profit for your units. And that's the solution. There was no solution. $1.50, you're never going to get to that place. I want to do a little bit of a tack-on explanation. I want to show why the $1.50 average will never be maintained or never be achieved, why $1.50 lies outside the boundaries of this problem. I want to have you get a feel of the relationship of numbers or the nature of these numbers. And using this graph is not a bad way to do it. This is still just the same graph that we were just talking about. And what we know is this is your cost curve. It never changes. The slope is always 4.5 or 450. It's $4.50 per unit, and our sales are at $5.50 per unit. And what we want to see why we'll never get to $1.50. There is a maximum we'll ever approach. I don't know if you can. You should be able to take a look at this. Pause the video for a second and figure out what the limit of the average is going to be. This is sort of an advanced analysis of why $1.50 is an impossible number. Start plugging in numbers that are very large. As the units go up, we've just been dealing down in the low thousands here. But if you go to 10,000 or 100,000, or hey, what if we just use 1 million? Like if we stuff in 1 million here, what we're going to find out is the way that this equation behaves is the 900 becomes insignificant when the x gets very large. That means that when we have 1 million units, we would have sold 1 million times $5.50. We would have sold $5,500,000 worth of product, and it would have cost us $4,500,000 to produce. The 900 becomes extremely insignificant, virtually zero in all this. The 900 started out as it's less than $1,000. Think about it. We're talking about millions. 5.5 million minus 4.5 million. The 900 gets lost in this equation at that point. At 1 million units, the average would then be 5.5 million minus 4.5 million, which is 1 million. Okay, so it would be $1 million. Go back to my pad here. Okay, so it would be 1 million at a sale of a million units. You'd have 5.5 million in sales. You'd have 4.5 million in costs, and so you'd end up with a million in profits. This is where we end up with. If you divide by the million units, remember that's what we started out with. The magic number is $1. That's the average. The average when we've gotten to $1 million worth of sales or profits here, when we've sold a million units, the average cost is just $1. It will never go above that. That's just the way that the nature of the economics of this problem are set up. It costs us $4.50. We sell it for $5.50. There always will be a $1 on average profit. It will at a very large number. It will always maintain out at $1. That's the max you're ever going to make. That is the point really worth bringing home. I hope most of you, got to this point following the videos and see why the way this was asked was really to bring out the explanation that I just gave. It's enough to say that the 1.5 million will never be reached. It's an impossible equation where units have to be positive. We ended up with whatever that ended up being is x equals, I don't know what it would come out to be, big 18, whatever the number was, 1800. But it was a negative number over here for the number of units. It's impossible to have x be negative. They gave us a number that will never happen. And what I just wanted to do is follow up again once more with what is the maximum you're ever going to hit for the average cost of the unit. Hope that's helpful. Thanks.